Hello, good evening. Can you see the screen and can you hear me? Can you now confirm whether I am audible? Okay. Since one more class is going on from 6 p.m. to 8 p.m., I am not expecting much participation now in this. I did not know one more class is there. We'll wait for some more time and then we will start. Maybe at 7, not 7, at 8, some more people might join. So as I mentioned last day, yesterday, that not tomorrow, next Monday there is no class. 25th there is no class. Our next meeting will be on 1st April. Okay, 1st April Monday will be our next class. As usual, 7 p.m. Alright, then we will start. No point of wasting time here. Since the recordings will be present in YouTube. I am expecting not a very long session today because no new concept to discuss. It's about the same concept that we derived and discussed last day. So just to repeat them, that torque at any slip of induction motor by the peak torque is related as 2 alpha s by alpha squared plus a squared, where alpha is the slip at which the peak torque is achievable and s is the other general value of torque. So this is alpha, this is slip, this is peak torque, and if this is some other general value of torque T, then this is S. This is S. So this S can be anywhere on the plot. And we have also seen that on the inclusion of rotor resistance, the torque speed characteristic of the motor changes like this. Sorry. Changes like this. The peak torque does not change. The peak torque does not change. The slip at which the peak torque is available changes. Means with increasing rotor resistance, we get the peak torque at lesser speed. we get the peak torque at lesser speed, and it is possible to have a certain calculated value of the rotor resistance such that we get the peak torque at the very starting of the machine. Starting is when we need the maximum torque or very high torque, because that is when it is required to break the inertia of the whole system, not only the motor but also the load. So it's desirable to have a large torque at the starting. Okay. One more thing that will come handy in today's discussion. One thing, just quickly derive a relation. That is, suppose mm, suppose R2 is changed. Okay, the new R2 primed is K times the old R2, KR2. Okay, so R2 is changed such that it is K times the older value. Now we know that the peak torque does not change. Peak torque does not change. Now suppose when the rotor resistance was R2, some certain value of torque would appear at a certain value of slip, S. Now when it is R2 primed, at what value of S will it appear? At what value of slip will it appear? Or in other words, if I say that the same value of torque appears at certain value of S prime, then what is the relation between S and S prime that we are going to calculate? Now, what we have is T by Tp is 2 alpha S by alpha squared plus S squared. This is the older value before changing the rotor resistance. Right now, Tp is same, and we are trying to find out when this T is happening in the new case. Now, since alpha is R2 by X2, the new alpha primed is simply K alpha. So 2 times alpha prime S prime if I write by alpha prime squared plus S prime squared, we can write 2 K alpha S primed by S prime squared. Now, if you so let us write from here again. It can be done simply from an investigation of this equation, or you can do some calculations also. So if you divide the sides by alpha squared, what you will get is S by alpha by 1 plus this equals alpha squared I'm dividing by, so S primed, it's a K squared. Okay, here top and bottom I divided by alpha squared, here top and bottom I divided by K alpha squared, K squared alpha squared. So this becomes K alpha, top and bottom means numerator denominator, 1 plus S prime. You can simplify this, or just by investigation, you can say that if I replace S prime as Ks on the right hand side, we get the left hand side. We get the left hand side. So this is what we get. So what does that mean? That means if R2 is changed to KR2, then alpha, the sleep at which the maximum torque, the peak torque appears, is also scaled by the same factor K alpha, and any other general value of S for which a certain value of torque appears, that may be full load, half load, whatever. Any certain value of torque appears at S, that would appear at Ks. So this we will remember. This observation might come handy in today's problems, in other problems, whatever. Okay. Any question here, or we will start solving the problems? Okay, then we will start solving the first problem. You can stop me if you need. So, oh, I said last class that next we have problems on test. That is because I just looked at the first question and saw this resistance reactance. Well, I saw there is some questions on test, but no question on machine testing. Same peak torque and all we will be handling today also. Next week again we have induction machine, but that is a single phase induction machine, not three phase. That means we'll be left only 2 weeks to study synchronous machine, which is extremely low. It is impossible to cover synchronous machine in 2 weeks. We had one complete semester for synchronous machine. Okay. Actually, machine requires at least 3 courses. Anyway, so we'll start this problem. A 3-phase wound rotor induction motor has the following standstill parameters: rotor resistance and rotor reactance. Stator impedance, rotational loss, no load currents are negligible. So that means the circuit effectively looks like this. X2 R2 by S. Sorry, by S. They don't even talk about, they say that no load current is negligible. Anyway, this current at no load is negligible because S is almost equal to 0. So R2 by S is almost equal to infinity. So this current is almost 0 at no load. And even after that, they are saying no load currents are negligible. That means XM is also not drawing any current. Means XM tends to infinity. So we don't have to even consider this. So what we are left with is simply this. Okay. All right. So first question is estimate the slip at which the maximum torque occurs. So we have already done this. Alpha is R2 by X2. No, sorry. R2 by S is X2, yes. So alpha is R2 by X2, which gives, yes, as you mentioned in the comment, a 0.0429. That is 4.29%. Get the maximum torque. Now estimate the per phase resistance required to be added to the rotor to get the maximum torque at starting. So we want alpha to be equal to 1. So the peak torque at starting means alpha is equal to 1. Starting slip is 1. That means R2 should be magnitudinally equal to X2. Sorry, X2. X2 is 1.28. Now R2 we already have some value. So R2 external should be 1.28 minus what you already have, 0.055. This gives us some 1.225 ohm. They said in milli ohm, so 1225 milli ohm. So be careful about these things in the final exam, if you are at all appearing, because that will be numerical type answers and it will be checked by computers. Okay. The next question is estimate the minimum value of the per phase resistance required to get the half times the maximum torque at starting. Half times the maximum torque at starting, which means starting torque by peak torque is half. And we know that at starting S is equal to 1. So 2 alpha, sorry, by alpha plus 1, this is equal to 1. So what we are left with is alpha squared minus 4 alpha plus 1 is 0. And what we get is alpha is minus b plus minus root over b squared minus 4ac, b squared minus 4ac by 2a. So 2 plus minus, this is 12. 12 is 2 root 3. So 2 plus minus root 3. Now 2 plus minus root 3, one value is 2 plus root 3, which is greater than 1. That cannot happen, at least when we are operating in this zone, forward motoring. So we have to take the other value, 2 minus root 3. So the feasible value of alpha is 2 minus root 3, which comes out to be 0.267. So this is the new value of alpha that we need so that we get half the peak torque at starting. Now this is equal to R2 by X2. So what is the new value of R2? So since R2 carries some meaning, we will write R external. So R2 plus R external is 0.267 times X2. That is how much we need there, total 1.28. This is what we need. So R external becomes what we need minus what we already have. That gives some 0.287 ohm. Again milli ohm, so multiply with 1000. Okay. With this, we will proceed for the next question. After the addition of the extra resistance to get half times the maximum torque, find the ratio of new starting current to starting current of the original motor. Now, today we have um, the circuit to our disposal. E2, as discussed, does not change. X2 R2 by S. So simply if we say that new starting current by the original starting current. So I start new by start original. So this will be E2 by square root of starting current. So S equals 1. So how much was this? 1.28. 1.28 squared plus 0.055 squared. Sorry, this is the older one. This is the older one. What is this? The new one. 0.26 plus 0.26 times 1.28. 0.26 times 1.28. 0.338. So this is the new resistance after adding the external 0.338 squared. This is the new current. So by the older current. 1.28 squared plus older value 0.0 squared. So this calculation will give you some 0.9697. So starting current has reduced. Okay, starting current has reduced by 3%. Any doubt till now? Okay, if not, then we'll go for the next question. A three-phase wound rotor induction motor runs at 1.5% sleep at full load. 1.5% sleep at full load. Stator impedances, rotor losses, no load current are negligible. So same conditions as before. Now the per phase rotor resistance is made 2.5 times of the original resistance by adding some external resistance. Load torque is kept constant. Estimate the new full load slip in percentage. So this is what we had a discussion. Let us look at it once again. The per phase rotor resistance is made 2.5 times of the original resistance. So this part I will just copy paste once. So what we have is K is 2.5. K is 2.5. Now estimate a new full load slip. Previously full load slip would occur at 1.5%. So S was 1.5%. So S primed will be Ks. So that is 37, 3.75%. We just used relation that we have already derived before. Yes, 3.75. Okay. Estimate the ratio new full load rotor current by original full load rotor current. So values are given. New full load rotor current by original full loads. R2 X2 values are not given. Let us see. Okay, it is not required. See one thing. Say this is the circuit X2 R2 by S. Say okay, full load. Full load. Sorry. Old. And the new circuit X2 does not change. R2 again, this is also at full load. New. R2 was made KR2 and we have seen that full load sleep is KS. So it becomes R2 by S. So the circuits are same. What we are seeing is full load equivalent circuits are same. So this can be one takeaway from this problem. This observation, if you remember, you can use that the circuit remains the same. Since the circuit remains the same, currents are same. That means the ratio is 1. Ratio is 1. Okay. Then we will go to the next sub question. Estimate the ratio new full load rotor copper loss by original full load rotor copper loss. Now full load currents are same. Rotor copper loss new. This is I2 squared times KR2. This is also I2 squared. We have seen currents are same. Sorry, not KR2, R2. So the ratio is K. 2.5. Is 2.5. Okay. Next part is estimate the ratio new full load output power by original full load output power. So output power is 1 minus S PG and 1 minus S PG. PG is 3 times I2 squared R2 by S. 1 minus is PG. PG is 3 times the total loss. So it is yes. So if I now find out new full load output power by origin of output power. So P output new by P output original. P output new is 1 minus Ks times 3 I2 squared Kr2 by Ks divided by 1 minus S times 3 I2 squared R2 by S. So this part goes away. What we are left with is 1 minus Ks by 1 minus S. Ks we found out some time back, 3.75. So 1 minus 0.0375 by 1 minus S was how much? 1.5%. So this will give you some 0.978. Okay, we're almost done for today. 4 more questions left, and we're only 37 minutes past the beginning. 30 minutes, because we have already established all these theories in the last class. So all we have to do today is just use the problems, and today's problems are much easier. We are not even handling with speed, power, because phase frequency, not phase frequency, pole is mentioned nowhere. So consider a three-phase induction motor with negligible, again same thing, stator impedance, rotor losses, no load current, and they have given some ratio this time: maximum torque by full load torque, maximum torque by starting torque. They have given. Estimate the slip at which the maximum torque occurs. This one looks easier to start with because we have only one variable here. Since we have to find out alpha, this equation will have only one variable, because at starting slip is equal to 1. So notice one thing, this thing is TP by TS. Okay, we are doing the opposite till now. So the ratio is TS by TP is 2 alpha S by S squared plus alpha squared, S equal to 1 since we're talking about starting, so 2 alpha by equal to half. So we have got the same equation that we got some time back. Some time back we got the same equation. Send our did I not? Oh, this is 1. This is 1. Alpha is 2 minus root 3. That is 0.268. So alpha is slip at which the peak torque occurs is to 26.8%. Okay. Estimate the full load slip. Full load slip. That is, now we have the value of alpha. Now T full load by T peak is 2 times alpha is 0.268 times S by 0.268 squared plus S squared. That is T full load by T peak, which is 1 by 5. Let us do it in a simpler way. The value of alpha makes this equation dirty. 2 alpha S by alpha squared plus S squared if I write. We have to find out S. So S squared minus 10 alpha S plus alpha squared equals 0. Take alpha as a constant. Then what you get is S equals minus B plus minus root over B squared minus 4AC by 2A. Then 5 alpha plus minus becomes 96. 96 by 4 is how much? 24. Ah, 4 root 2 root 6. Alpha. So 5 plus 2 root 6 is definitely bigger than 1. We cannot take that. How much is 5 minus 2 root 6? 5 minus 2 root 6 comes out to be 0.1010. 0.1010. If it so happens that, say, for somehow this solution gives you two values of alpha, both of which are less than 1, then another thing or another condition that can save your life there is that alpha is always greater than S full load, because peak torque happens at a speed lower than the rated torque. So this condition also you can use. In this case, we need not at all. Okay. So 1/10 of what we had before, 0.101. So more or less we will get 0.027. So 2.7% is the full load slip. 26% is the peak load slip and 2.7% is the full load slip. Sorry, peak torque slip. Okay. And the next question is estimate the required percentage reduction in rotor resistance to bring down the full load slip to 1%. So basically there is an assumption that at the very beginning itself there was some resistance connected, because there is no way that you can reduce the resistance of the rotor circuit. So definitely there was something. Or is it possible to reduce the rotor resistance? It may be possible if hypothetically you feed some power to this circuit. If you feed some power to this circuit, that will reflect it as a negative resistance, negative external resistance. So either of them, either an assumption that at the very beginning itself some resistance was connected, or maybe you do this. Now the circuit that I showed last day, a diode bridge rectifier right after the rotor circuit will not work. If you want to do this, what you have to have is an inverter. Now this may look a little bit confusing, because this side is AC, another side is DC, and since we are sending power back, that's why I'm saying inverter. Now basically this circuit is a very general circuit. Depending on how you control it in the DQ domain, you can have power on both directions. This is also called as AFE, active front end rectifier. Depending on how you control this, you can have power flow on both directions. So if you have a circuit like this, so DC here, maybe another inverter, followed by three-phase transformer, to the grid. So in this case, it is possible to effectively reduce the resistance of the rotor circuit. Okay. So again, you see, it's all about flowing, all about the flow of the slip power. Here the slip power becomes negative. It's going into the rotor. Now, what are we getting at all if we do that? There are actually very fascinating theories, fascinating research works done on this, that you originally had this, now you have something like this. Something like this you have. Now if I zoom into this area, so the red curve falls like this, and the green curve falls like this, right? Synchronous speed. So the same torque, same load torque TL now appears at higher speed. How is it possible? No, okay. Same torque TL now appears at higher speed. That means your output power is increased. Same torque happening at higher speed, your output power has increased. How come? Because you are feeding some power into the rotor. That power is also now going to the mechanical side. Now, one little concept here, maybe a food for thought. Suppose, forget all the losses for now. You have the stator, okay? Then should not draw like this. Some isolation through the air gap. You have the rotor, and the rotor delivers mechanical power. Okay. Now suppose this induction machine is rated for 5 kilowatt. Forget all the losses for now. So 5 kilowatt you give in, 5 kilowatt goes out. And what you get here is also 5 kilowatt. Now here you see one thing, that although not although the stator and rotor both are rated for 5 kilowatt, both can handle 5 kilowatt. Is it not possible that we give 5 kilowatt to the stator? Is it possible that we give 5 kilowatt to the stator, since it is rated for 5 kilowatt, and by this scheme we give 5 kilowatt to the rotor also, and at the output we get 10 kilowatt of mechanical power? Is it not possible? Now one um, doubt might be coming up here, that the rotor is now handling 10 kilowatt of power. One question might be coming up, but you see here one thing. What I was thinking is, it's all about, see, this current you do not change. Instead of short circuiting this terminal, you have increased the voltage such that there is a reverse flow of power. Are you saying something? Okay. So the rotor current does not change. There is some research work on this, some rigorous research work, not some. There you can see. Anyway, so that is not our topic of discussion. Estimate required percentage reduction in the rotor resistance to bring down the full load slip to 1%. So S primed by S primed is 1% and S is 2.7%. S is 2.7%. So what we are getting is S primed is 1 by 2.7 times S. So our K is 1 by 2.7 in this case. So R primed will be 1 by 2.7 times R. Question is percentage reduction in rotor resistance. So what we have to find out is percentage reduction. So R minus R primed by R. Let us do something here. R by R primed by R is 1 by 2.7 So if I subtract 1 from both sides, 1 minus r, sorry, like this, 1 by 2.7, it is percentage reduction. So obviously with respect to what we already had, so 1.7 by 2.7, this should give some 0.63, that is 63%. Okay, now we'll look into the last question of the day. After the rotor is redesigned with the reduced resistance, estimate the value of new starting torque to previous starting torque. We don't have any value of starting torque, but the only factor that can help us relate between these two situations is the peak torque, because that remains the same. So for the new case, the starting torque Ts prime, if I write, by the peak torque is 2 alpha primed by alpha squared plus 1. So alpha primed squared plus 1. Now we know that alpha primed is k alpha. So 2 k alpha by k alpha squared plus 1 is the new. And the old one, what we already have is Ts by Tp is 2 alpha by alpha squared plus 1. Alpha do we know? Alpha we know 0.268. K also we know. So then we can find out. So new starting torque by old starting torque, that is ratio of these two ratios, since Tp does not change. So it is 2k alpha square plus 1 times 2 alpha gets cancelled. K remains k alpha squared plus 1 by plus 1. K is 1 by 2.7 and alpha is 0.268. So substituting the values should give the final answer. It should be how much? K is 1 by 2.7 times alpha is 0.268 squared plus 1 divided by k alpha 0.268 by 2.7 squared plus 1, 0.393. So that is the ratio of new starting torque before the reduction of rotor resistance and what we had originally. See, this is again supported by this graph. The green one has lower starting torque. Okay. So that's all for today from my side. Now, if you have any question, I will answer, or else I'll wait for some time and then close the session. Ratio of copper loss in this problem. What did we have in? Hello.
Yes, sir.
Problem what we had. Let us read the problem once again. The three-phase downloaded induction motor runs at this much slip at full load. Increase the rotor resistance by 2.5 times of the original value by adding external resistance. So, okay, this part is understood, that increment of the rotor resistance by certain factor and then running the machine at full load torque does not change the rotor current.
Yes, sir.
This is understood. So before and after the increment of the rotor resistance, the full load current does not change, right? So I2 squared, I2 squared, I have written both the cases. For the, oh, I wrote dash both the
Yeah, yes,
cases.
sir. This R2 by KS2, it should be like that.
No, no. See, this is the actual rotor circuit without doing any jugglery. True?
Yes.
Without doing any jugglery. Now, the current is this. We divide by S. What we get is squared. So this circuit equivalently we can draw like this. Draw like this. What is the advantage of drawing the circuit like this? Is that E2 does not change with frequency. Impedance does not change with frequency. That means reactance does not change with frequency. That means this circuit is now frequency independent. Whatever circuit we had at the starting, same circuit we will have at any speed. That means the frequency of the stator circuit and the frequency of the rotor circuit are same. That means we can draw the equivalent circuits together where power flow is possible. We had this discussion, right, that different
Yes, sir.
frequency
Yes, sir.
sources cannot have non-zero power supply in between them, non-zero average power supply in between them, right? So if we do this, we can conveniently draw the induction motor equivalent circuit like this. That's why we did this jugglery, so that this rotor circuit becomes frequency independent. Now, you see, before and after doing this jugglery, this I2 value did not change. I2 value did not change. I2 is still flowing as before. That means I2 is still flowing through a resistance R2. So what the circuit looks like now, the rotor circuit is actually like this: R2 1 minus 1 by S. You can think it in this way also. Okay, let us complete this discussion. So this I2 does not change after doing this jugglery. So the rotor copper loss is I2 squared R2. This is the rotor copper loss. And if you do I2 squared R2 by S, that is the per phase air gap power. So before the jugglery, again you can have a question here. Before we did this, if we put these two circuits side by side, before we did this, when we had X2 SX2 R2 AC2, then what would happen with the change of load? I2 would change, AC2 would change, so the power PG AC2 I2 would change. And for the next case, how would we take care of the power? It is X2 R2. We take care of the changing power by this term. This term. That is why this represents the developed mechanical power. The rotor resistance did not change, and the current through it also does not change. So the rotor copper loss is still this. Before and after the jugglery, the current did not change. So I2 is still flowing through R2. So it will be R2, not R2 by S. Is it clear now?
Okay, sir. Okay.
Okay, anything else? Do we really have synchronous machine in this course? Let me just check quickly. Week 10, we have single phase induction machine. Yes, synchronous machine. We have a little bit last 2 weeks. Okay, if you are done, you may stay or you may leave. Whatever, I will wait for some more time. Hi Neeraj, we have completed today's discussions. So you want me to go through it once again, or can you hear me?
Yes, sir, I can hear you, sir.
Okay. So we started at 7 though. So you have some specific doubts.
No, sir.
Um,
Sir, I was absent in few sessions because I was sick, sir. I haven't joined.
that's okay. You can go through the recorded videos in YouTube. All the sessions are uploaded in YouTube.
Okay, sir. Sir, when will this session be uploaded, sir?
See, I take the sessions every Monday from 7 p.m. to 9 p.m. But next week I'm not gonna take the class. That's why for only one class I preponed it to today. 25th March class I preponed to today. Otherwise,
Okay,
I
sir.
take classes every Monday 7 to 9. So again, from 1st April, I will take classes on Monday. 1, 8, and 15. Three more classes are left.
Okay, sir.
And if you want to see the recorded lectures, they are present in
Sir,
YouTube. I will, yeah.
can you give a short summary for this session?
See, the fundamental basic means the basics of today's discussions are actually established in yesterday's class, the regular Monday class. It is mostly based on the relation between the maximum possible torque an induction motor can provide and how much torque it is providing at some other operating point. The maximum possible torque that the induction motor can provide, if you look at this graph here, if you look at this graph here towards your right hand side, that can that the induction motor can provide is much higher than its rated torque. Okay, so if say Tm is here, say TL is here, load torque, rated torque, sorry, not load torque. Tm, why did I write this? I think I wrote it opposite. Tm is greater than Tr. Maximum torque is much higher than the rated torque. The induction machine can deliver that much of torque, but the windings are not rated for it. Windings are not rated for it for the same. Now, given that we here derived this relation here, that if alpha is the slip at which the peak torque appears and S is any slip, any general value of slip where any value of torque T appears, then this is the relation of the developed torque and the peak torque. And alpha is given by the ratio R2 by X2. This comes from maximum power transfer theorem. So this was the basis on which all the problems of last day was based, and all the problems of today also we did from this. One small thing we derived at the beginning of the class is that suppose you change, one more thing is this graph, that you are changing the rotor resistance. What happens is the peak torque capability of the motor does not change with the rotor resistance. Rather, the slip at which the peak torque appears, that is alpha, changes. Since alpha is R2 by X2, you are changing R2, means increasing R2 will increase alpha. So at higher and higher value of slip, you will get the peak torque. Slip increases from right to left. Here you have slip 0, here you have slip 1. So in this way it increases, but the peak torque does not get affected. That is clear from this equation. Now, based on this, what we derive today is, suppose we increase the value of R2 by a factor k. So the new R2 prime is k times R2. Okay. Now the question is, when the resistance was R2, rotor resistance was R2, some value of T, some value of torque used to appear at certain value of S. Now with a new R2, the same value of torque will appear at some other value of S primed, other value of slip. So what is the relation between S and S prime? So to do that, we are finding out T by Tp for both the cases. Now since Tp is same, peak torque is same, and we are trying to find out the slip for the same value of torque. So these ratios are same. So we can write 2 alpha S by alpha squared plus S squared for the previous case, and the new case alpha prime S prime and all we know is, since R is R2 prime is k times R2, alpha prime is k times alpha. And on simplifying, what we get is S prime is ks. That means if you increase R2 or maybe change R2 by a factor of k, then alpha, that is the slip at which peak torque appears, also gets changed by a factor of k, and the slip for which any value of torque appears changes by a factor of k. That means if previously you were getting 10 Newton meter torque at S slip, now you will get 10 Newton meter torque at ks slip, like that. Okay.
Okay, sir.
Now based on this, we solved some problems. So today's problems are actually much easier than what we had yesterday. Yesterday it was a little bit more rigorous. Today's circuit parameters are given, and see, first we find out the slip at which the maximum torque occurs, which is R2 by X2. Then what we want is some calculated value of resistance we want to add to the rotor circuit, such that we get the peak torque at the very beginning itself. That means alpha is 1, because at the starting slip is 1, so alpha is 1, so that we can get the peak torque at starting. That means R2 should be equal to X2, which is 1.28, already given in the question. Now we already had this much resistance, 0.055, so the rest we have to add. So if we add this much resistance to the rotor circuit each phase, we will have the maximum possible torque at the starting itself. Now estimate the minimum value of per phase resistance required to be added to get half times the maximum torque at starting. So now we want half the maximum torque at starting. So starting torque by peak torque ratio is given by 2 alpha by alpha squared plus 1, because S is kept, S is 1 at starting. So in that expression, if you put it S equals 1, you get this, and this is given as half to be added to get half times the maximum torque at starting. Now you've solved this, and the graphs tells us that alpha is always less than S, because peak torque happens at much lower speed. Sorry, not less. Peak torque happens at lower speed than the full load torque. So alpha is higher than the full load speed. Lower the speed, higher the torque. Sorry, lower the speed, higher the slip. So this is the thing that gives, that means using this condition, we can eliminate one solution of the quadratic equation, and we finally get some value of how much external resistance we need to have half the maximum torque at starting. Now the question is, how does the starting current change So this is the circuit. Starting means S equals 1. So simply two resistance values, just find out the current ratio like this, you get this. That's it. Now next question is same, more or less. It is given full load slip is given, and per phase rotor resistance is made 2.5 times. So this relation what we derived some time back will be of help here. So K is 2.5. Full load slip was 1.5. Now what is the full load slip? It is Ks. Just multiply with K, you get this. Next one is full load rotor circuit current by the original full load rotor circuit current. Now see, the left one is the older rotor circuit, X2 and R2 by S. New one is the right one is the new rotor circuit, both at full load. Now R2 has become KR2, and since both are at full load, S has become Ks. So you see, these two circuits are essentially the same. That means they will draw the same current. So the full load current does not change with introduction of rotor resistance. The ratio is 1. Now since the currents are same, but the resistance has increased 2.5 times, so the copper loss is now 2.5 times of what we had before. Okay. That's it.
Okay, sir. Thank you, sir.
And output power ratio, just we have used the formula. This 1 minus S times 3I2 square R2 by S. The two cases where S is Ks, R is Kr. Just put them and found out the ratio. Cancellation gives us this. Put the value and get this. And the last one asks us three-phase induction motor with negligible state impedance, rotational loss, and no load current. Some ratios are given: maximum torque to full load torque and maximum torque to starting torque. What is the max slip at which maximum torque occurs? So starting slip is 1. That's why we can write starting torque to peak torque ratio as 2 alpha by 1 plus alpha squared. Now estimate the slip at which maximum torque occurs, that is estimate alpha. We solve this equation and get the value of alpha. Now since we have the value of alpha and since we have the ratio of full load torque to peak torque, we can again solve this equation to find out the full load slip. Okay. And this one is percentage reduction of rotor resistance to bring down the full load slip to 1%. So again, these concepts are coming into play. Now full load slip they want to bring back to 1%. Initially we had 2.57%. So new slip by old slip is 2.7. That is that constant or that factor K is now 1 by 2.7. So since the factor is 1 by 2.7, the resistance is also multiplied the same by the same factor. So R prime by R is 1 by 2.7. Now from here you have to simply find out this thing, since you have been asked to find out the percentage reduction. Just this factor you have to find out. From this you get 63% reduction. And finally, new starting torque to previous starting torque. Now starting torque values and all we don't have, but only thing that links us between the previous case and the current case is the peak torque, because that remains the same. So we have to do something in relation with the peak torque. So both the cases we find out the relation of starting torque to peak torque, and then we find a ratio between them. That gives us the relation between the two starting torques. And we get this K and alpha are known. And we finally get this ratio. That's all.
Okay, sir.
You go through the videos. Machine 2. I think you already have the link to the playlist, all the playlists
Yes.
of all the videos.
Sir, I think I have to go through the textbook, sir. Watching the videos takes a lot of time, sir. I have to cover that or which I have missed, sir.
Okay, you can. But these sessions are only problem solving and doubt clearing. Okay, these are not lectures on induction machine. If you are ever going to learn induction machine, these videos are not for learning induction machine.
Yes,
This is
yes.
when you have already learned and then solving problems, then having doubt. These sessions are for that purpose.
Yes, sir. These instructions were given in the first class, sir. I remember it. Okay, sir.
Okay,
Okay, sir. Good night, sir.
good night.